So, hello everybody. So if we can start back again. So today we want to talk also about this pipelining in sklearn, because in sklearn we can build this pipeline in machine learning, and it will help us to make our work more professional and more easy. So we need to understand this pipelining, and in this pipelining, it's an approach where we can combine many different steps in one step. So it will we will make it easy for us to try to optimize the hyperparameters of our models, because I mean in machine learning we can start with maybe data pre-processing, scaling, standardization, for example. Maybe we need to do some principal component analysis. We need to select the most important. We can use sklearn select best K, for example, which help us to select the best subset of features, for example. Maybe you can do some feature engineering stuff. So the idea here is to use this pipelining to try to make our work more efficient using this pipelining. So in sklearn, we have a very nice tool which can help us to do this pipelining very efficient. So the machine learning pipeline, it's created to allow data flow from its raw format to some useful information. We do this all the time. So for example, we are working with some raw data to do some regression or some classification. So the pipeline, it will help us to facilitate this data flow from its raw format until we have some useful information, which could be classification or regression, for example. It provides a mechanism to assemble several steps that can be cross-validated. I mean, it's very important also to cross-validate our different steps while setting different parameters, because maybe I need to select a different subset of features, maybe I need to select different number of principal components. So it would be nice to combine all those steps together and try to train the whole pipeline, so we can try to cross-validate all those steps together. It improves the performance and the organizations of the entire modeling process from data into model production. It helps us to be more efficient, starting from data until we have a model, for example, and it supports scalability, for example. So it consists of, for example, it could be, we have a model here in the middle. So I need to go back again. How can we, okay, so we have here deployed model. I mean, we have a model, right? And this model, we need to train this model, correct? We need first to train this model, and after that we will deploy this model, and maybe before that we need to validate, test and validate this model. But also we have some, maybe we have some historical data. We are working with historical data. We will use also historical data for training our model, but we will not use those historical data as they are, for example. Maybe we need to do some feature scaling, or we need to do some scaling or some data pre-processing, correct? Standardization or scaling, for example. Maybe we need to do some feature engineering. So I have some features, maybe I have feature 1 and 2, x1 and x2, and I need to create a super feature which will help us to simplify our model. So we can just apply some feature engineering stuff here. It could be maybe principal component analysis. It could be select k-best, for example. This function, which is a nice function called select k-best. I need to select the subset of features, for example, principal components. So we can have the principal components, but we need to select how many principal components we need. This is a hyperparameter. And also when we're using select k-best, also this k also is a hyperparameter. Should we select k equal 5, 4, 3, 2, 1? Which one should we select? It's the same for principal component analysis also. How can we select n, for example? Should we select 2, 3, 4, 5? It could be a hyperparameter. Maybe standardization and scaling. We need to put standardization and scaling here, so we can convert, or maybe those are images and we need to divide each pixel value by 255, for example, to be in the range between 0 and 1. So there are many things which we can do it here. So and after that we need to select a model selection. I need to select a model in the pipeline. The best thing in the pipeline, I can build a pipeline and I can select different models in this pipeline. And it could be also a hyperparameter. Should I go for KNN? Should I go for a perceptron? Should I go for MLP? So it could be also selecting the model and testing different models. So at the end, I will get the best combination of those approaches together. At the end, I will deploy my model. And then when we deploy our model also, we will still working with some data, but it will not be historical data, but it will be stream data, for example. Maybe those data are coming from some sensors in real time or cameras, for example. So I need to apply those sensory information or data to the feature engineering, the same feature engineering here. So I can have a subset of features, and I will apply those subset of features to my model, and I will get some scoring here or classification, regression, whatever. So when we do this pipelining, it will help us to be more organized, more compact, so we can cross-validate different steps or different functions together, so we can get the best combinations of hyperparameters at the end. So the pipelining, it makes your workflow much easier to read and understand, and it enforces the implementations and order of steps in your project, because we have some orders, we have some steps which we need to follow. For example, if I'm working with historical data, we need to do some scaling first. We need to do some dimensionality reduction, correct? It could be by principal component analysis, whatever, or autoencoder, for example. After that, I will select a model, and I need to fit this model. I need to train my model. And after doing this, I need to have a predictive model, which can be used for predicting some stuff, applying some stream data, for example, to those models. So there are some steps which we need to follow, and having this pipeline, or developing this pipeline, it will enforce us, in fact, to be more organized and to follow the order of steps as it is known. So it makes also your work much more reproducible. So once you build your model as a pipeline, it will be easy for other people to just retrain this pipeline instead of running different steps. Maybe I have a problem in one of those steps, but when we have our work compacted and into this pipeline, it will be easy for other people to understand our work and also to reproduce our results. It consists of transform, fit, and predict. So it consists of those three steps: to transform, fit, and predict. Transform, because I have some data, and this data, maybe it's in raw format, for example. So I need to transform it from that form into my features. So maybe I need to do some scaling, some standardization, for example. I need to apply some dimensionality reduction, feature selection, feature engineering. So all those are included into transform. We need to transform the data from its raw format into another format, which will be applied to my model. And after selecting a model and adjusting the hyperparameters, I will fit my model to those data. And after that, I will have a model which can be used for doing prediction, right? Because we need to predict, so we can apply our test set and we can validate our model. So we will have an example with this iris data set. If you need to use just without a pipeline, for example. So we have a data set. Data sets, we import it from sklearn. And from this data set, we will import iris. So iris equal data sets to load iris. And we know this iris data set, it's a data set which has feature input features and one target feature. And there's a target feature consists of 3 classes, as you can see it here. I try to plot those 3 classes against sepal length and sepal width, for example. We have 3 classes, as you can see it here. One class is far away from the other 2 classes. The other 2 classes are more challenging because those 2 other classes are too much overlapped. After doing this loading and plotting your data set, you need to use maybe train test split, because I need to validate my model. So if you will use hold out validation, I need to use this function, which is train test split. We need to import it from model selection. So the input to this function will be x and y. X will be the input features, y will be the target features. We need to use this random state equal 42, for example, because it will help us to shuffle. Because this function, it will shuffle the data. And if you need to reproduce, if you need to get the same training set and the same test set later on, you need to define this random seed, for example. We need stratify, and the stratify equal y. We will use this stratify equal y to be able that our classes are stratified, which means are equally divided between the train set and the test set. So for example, here I have 50 and 50. We will use the first 2 classes, for example. No, it's 3 classes, 0, 1, and 2. So in this case, 37 from class 0 will be, the train set will consist of 37 from class 0, 37 from class 1, and 38. It should be also 37, but sometimes it's not exactly divided exactly equally between those classes. And also in the test set, the 3 classes, we can see that the 3 classes are equally represented in my test set. if you want to get this count, you need to use this function bin count. Bin count y train, bin count y test. So when you do bin count y train, you will get those numbers. Bin count y test, you will get those numbers. So of course we do it for the labels or the target features, because we need to know how many different classes in each of y train and y test. If you want to use principal component for dimensionality reduction, in fact, we use it to get some principal components. We can use, we need to define principal component. You need to define number of components or number of principles. Here I selected 4 because the set consists of anyway 4 features, x1, x2, x3, x4. So this is the maximum number, which is 4, for example. And you can fit this principal component with x. It's only with x. In fact, it's unsupervised. So principal component analysis, it's unsupervised technique and supervised. We are not working with the target features, we are working with the input features, right? So, we can calculate also the explained variance. So it will be BCA.explained variance. You can multiply it by 100, for example, to be in percentage, and you can print those numbers. And at the same time, also, you can plot those numbers. Or you can just use cumulative sum of the explained variance if you want to plot it, which means this graph here, we are plotting the principal components. Here we have 4 principal components. Principal component number 0, principal component number 1, number 2, and the number 3, as you can see, because we have 4 inputs here. So maximum we can get 4 principal components. This number here, it means using only one principal component, this one, it can explain around 90% of the information of the data. So in fact, in this classification problem, I can solve it using only one principal component, which means using one principal component, it will explain 90% of the variance in my data set. And if I will use only this one, we will lose 10%. So of the knowledge or of the information from my data set, if I will use only one principal component. If you will use 2 principal components, so in this case, the first one will explain maybe 90%, the second one, maybe it will explain maybe 6%. So in this case, in fact, this is the cumulative, right? This number, which is close to 100%. Correct? Do you see this number? So in fact, it's like 90 plus 6, it will be 69% or something. So if I will use the first 2 principal components, we will get around maybe 96% of the information. We will lose only 4%, right? So the idea here is to try to use principal components and dimensionality reduction, because instead of using four input features, I will use only 2, and those 2, it will still give me 96% of the information. So we will lose 4%. Maybe we will lose around 4%. If you want to use more, maybe you can just decide to use the first 3 components, and in this case, you will get around 100% of the information, right? So if you will use principal component 1, principal component 2, principal component 3, in this case, you will maybe have 99.9% of the information. And in this case, instead of using 4 inputs, I will use only 3 inputs, right? So this is the explained variance. The first one, it will explain, we cannot call it x1, in fact. It's principal component 1, not x1, because it's not x1. And this one, it's principal component 2. This one, it's principal component 3. This one, it's the principal component 4. So in this case, if you use the first one, it will give you 92% or 92.5% of the information. If you will use only principal component 2, it will give you 5.3%. If you will use BC3, it will give you 1.7%. You can sum those numbers together, and it will give you around 95.5%, 99.5%, right? So in this case, using a principal component, it will help you to reduce the dimension. And when we reduce the dimension, we will build simpler models instead of using very complex models. Here, I will try to, we did that. And after that, I try to plot your classes against the principal components. So to see if it will make any difference. So this is the Sybil length and the Sybil width. So those are the data set. You can see here we have some overlap, right? And those 2 classes are close to each other, for example. So using Sybil width and the Sybil length is still difficult. Maybe if you can plot it against the beta length and the beta width, you will have better classification. So now it's much better when we plot the data set against beta length and the beta width. And this is how it will look like when you are plotting your data set against the principal component 1 and the principal component 2, for example. So we have better separation between class 2 and class 3, for example, better separation, because maybe this is difficult to understand. Maybe for this data set, it's simple and I can block my data set against better lengths and better widths. From those two graphs, you can see that building a model using better lengths and better widths, you will get much better results and your model will be much simpler than using simple lengths and simple widths, right? So this one is much better. But if you cannot reach this conclusion, maybe in this case, you can use principal components. And this is how it look like when we are using the principal. We didn't lose any information. However, we have also better separation between classes. So this one, we have better separation here, longer distance. And also, in case of class 2 and the class 3, we had too much overlap here, which is very difficult to divide. But in case of using principal components, I guess it's much easier to now to plot a line. And this line might give us maybe accuracy of maybe 95% or 97%, right? So using the principal components, it gives us very good advantage because we can simplify the model and without losing too much information. Now we need to create a pipeline in 4 steps. First, we need to decide what will be the components. First, we need to import pipeline from sklearn.pipeline. So this is my pipeline, right? So we need to import this pipeline from sklearn.pipeline. Model selection, you can, if you need to do cross validation, for example, we can use cross validation from model selection. We have also a nice technique called the grid search cross validation. Grid search cross validation. This one, it's a grid search technique which can help us to automate the process of adjusting or selecting or optimizing the hyperparameters of the models or the pipeline. In my pipeline, I want to use principal component analysis. So I need to define principal component analysis. I need to define a model. So maybe I will have a pipeline for a perceptron and another pipeline for SGD classifier. I need to use a standard scaler. It's a data pre-processing. So I will use this standard scaler, for example. We will use also min-max scaler. So we will use those 2 steps, right? I need to get all my features, input features between 0 and 1. And I need also using a standard scaler, I need to get mean equal 0 and variance mean equal 0, correct? Plus minus variance equal, I guess 1 or something. So I will use also a standard scaler. So I need to build my first pipeline. It's very simple, as you can see. So your pipeline, pipe 1 equal pipeline, you need to define your steps. So the first step will be min-max, right? So I just need to define min-max, correct? And the second step will be standard scaler, right? So I will do first. So in one side, this is my pipeline. And in one side, I will have this raw data. So once you have the raw data in, we will apply first min-max scaler. And after that, we will apply standard scaler. And after that, so the table of data here will be the same. It will be like this one. We have 4 features, x1, x2, x3, x4, and y. We will apply principal component. In this principal component, you need to define number of principal components which you want to use. Is it 2? Is it 3? Correct? And after that, the model. So my model I will use for one pipeline, I will use a perceptron. And for the other line, I will use adaptive linear unit, for example. So in this case, we do here transformation, fit, and the predict. Predict, we will do it after training, right? So this pipeline, we will do here transformation, data transformation, and after that, fitting or fit or training. And after that, we will do some prediction. So if you want to see the steps, different steps in your pipeline, you just need to print pipe1.steps. So I have here some steps, min-max. Step 0 sorry, min-max, it will be step 0, it will be the first step here, which is min-max scalar. So this is min-max. So the feature range, it should be between 0 and 1. If you want to play with the parameters, so you can do it here. So this is step 0. Step 1, it will be standard scalar. Step 3, it will be principal component analysis. Step 4, it will be perceptron, for example. If you want to change if you want to change the model parameters, you can just select pipe1.set parameters perceptron, because we define it here as a percep. So it will be percep underscore 2 underscores, this one. And this is the learning rate, eta 0 equal 0.5, initial learning rate equal 0.5. So you can do this, you can do some changes here, you can adjust those parameters, right? So you can play random state equals 0, for example, if you want. Shuffle, if you need to shuffle, correct? So So you can do all those stuff into your pipeline. So if you want, for example, to select 3 principal components, so I need to use pipe1.set parameters BCA 2 underscore. This one, it's 2 underscore n underscore components equals 3. So if I need to define, if I need to use 3 principal component, I need to define it here by pipe1.set parameters. The learning rate, for example, it will be percep 2 underscores eta 0 equal 0.2. So now I need to define the initial learning rate, right? So you can do this. And after that, I will use xtrain ytrain for training my pipeline. So it will be pipe1.fit. So now, in fact, we train not only my model, but the whole system. We cross-validate the whole system. So I mean, the idea here is to cross-validate all those different steps together, right? Not only the model, because maybe for principal component, I need to test my model for 2 principal component. I need to do this cross-validation again for 3. I need to do it for 4, for example. So when we try to combine all those steps into one pipeline, we will cross-validate all those steps in one step. So we will train our model. So first we will process this min max. It will take 0.0 second, for example. Second step, standard scalar, because we have here 4 steps. And after that, we will do BCA. So BCA also, it will take some time. This is step number 3. And finally, we will train our model, which is a percep, right? So this is a training time, training score, and the testing score, for example. It will be this time. After that, I want to do the confusion matrix. If you want to plot the confusion matrix, I need to run predict, correct? So we need to import this confusion matrix from scalar.metrics, maybe precision score, recall score, maybe F1 score also, right? Maybe accuracy score, correct? You need to do all this. Maybe, I mean, this classification report, it will be much easier. But before doing this, I need to get ypredict. To get ypredict, I need to use pipe1.predict of xtest. When we do it, you get ypredict. And after that, you can plot your confusion matrix and print also your precision score, recall score, for example, and all those numbers. So it's confusion matrix again for multi-class classification. Maybe I don't need to do this again, but we can do it quickly also. So this is, we have 3 classes here. We have 13 from class 0 classified for the test set. We do this one for the test set. So it's 13 from class 0 classified as 0. So the accuracy for this class 0 is 100%, right? So the accuracy and the recall here, we have here the recall precision. So the precision, it's 13 divided by 13 plus 1. It will be this number. For class 0, it will be 6 divided by 6 plus 2 zeros. So it will be 100% because 6 out of, in fact, it's 6 out of, okay, 6 out of 6 because this is the precision. From all predicted 1, we have 1. So the precision for this one, it's 100%, which is misleading, as you can see. For this one, it's 12 divided by 12 plus 6 plus 0. So it will be this number. And for recall, it will be 13 divided by 13 plus 2 zeros. It will be 100%. For class number 1, it will be 6 divided by 6 plus 6 plus 1, 46%. And for this class number 2, for example, it will be 12 divided by 12 plus 0, so it will be 100%. So now we have this individual or class-wise. We can say that this is class-wise precision and recall. We need to combine it to get this overall precision and recall, right? So you can just take the average, for example, or so it's a summation divided by 3, or it could be weighted sum, omega multiplied by omega. I mean, anyway, this is a combined. And of course, it would be nice if you want to get the accuracy. So the accuracy, it will be 13 plus 6 plus 12 divided by the total number, which is 38. Okay. We do this, in fact, not for. In this case, we do this one for yes, 13 plus 12. So this is the test set size, right? So it will be this. Yes. For pipe2, it will be exactly the same. So you have pipe2 dot steps. If you want to see what kind of steps you have, for example, if you want to set a parameter, for example, the initial learning rate, for example, you can do it. Fit, you can do it for X train, Y train, and you can get all those numbers again. We have the training set, we have the test set, training score and the testing score. So pipe1 dot score. So it will give you the accuracy for the training set, the accuracy for the test set. You can get the confusion matrix. So it will be pipe2 dot select model. Just deal with this one as a model. So the confusion matrix, it will be Y test and Y predict, or pipe2 dot predict of X test, for example. So this one, it will give you, it will return you Y predict. Correct. So the confusion matrix, we can see it here. And if you want to get the precision recall, precision recall, and also, so have this function precision score, recall score, F1 score also, you can get those numbers, you can get all those numbers. We used here this average equal weighted because we need to get so this one, if this one is none, average equal none, you will get the it's a class wise, right? So you get the individual classes, the precision and recall for individual classes. If it's weighted, it will be weighted, right? We know how to get weight. So the problem now, we build a pipeline and we need to automate the process of adjusting the, we need to find a way to use this grid search, and this grid search, it will help us to adjust, to select the hyperparameters, to optimize the hyperparameters. So in this case, we need to find a way for doing this. So we will use grid search. Grid search, it's exhaustive search over specified parameter values for an estimator. So, I mean, number of candidate models, that's up to you because it's according to the number of parameters. So, for example, we will start here by selecting importing grid search cross validation. Okay. So, we will use this. Okay, sorry. Why you are not cannot? Do you see this grid search? We need to import it from model selection. First, we need to import it. So we need to we need to define the parameter grid. It's a dict, which is dictionary, for example. So, for example, I need to check for the principal component. I have principal component, so it's a principal component PCA 2 underscores n dot component. I need to check for 1, 2, 3, and 4 because I have 4 parameters. I have 4 input features, so I need to check. Should I select one principal component? Should I choose 2? Should I choose 3? Should I choose all of them? So in this case, I will have this n components equal 1, 2, 3, and 4. So I will test this one. I will cross validate this one 4 times. 1 time for n components equal 1, 1 for 2, 1 for 3, 1 for 4. I need also to check the initial real learning rate for the perceptron. So it will be percept 2 underscores eta 0. I need to check it for 0.2, 0.5, 0.8, 1. Right? So in this case, I will have 4 values for initial learning rate, and I have 4 values for the n components. 4 times 4. So in total, we have 16 candidate models. So first, I need to check this one for this 0.2, 1 with 0.5. Which one will give me better score? For 0.8, 1, and I go to the second, and I repeat this process. So in total, we will have 16 combinations of models. So I will use this grid search CV, and I will do it for pipeline 1. And this is the parameter grid. Parameter grid equal parameter grid. Cross validation equal 5, because I need to cross validate all those together. So I will divide my data sets into 5 folds. And the scoring, which we will use for, I mean, comparing between those different combinations, we will use accuracy, for example. You can use accuracy, you can use error, you can use precision, recall, and so on. So after that, we will train this model using, in fact, this one should be not X train, Y train, it should be just X and Y, right? Because we use cross validation, so you don't need to use X train, Y train, you can just use all X and all Y. So grid search.fit using X and Y. And in this case, we will print best parameters for which, I mean, accuracy score, for example. So we will do it, and we will get, and also, we can also print grid search dot best parameters. And when you have those best parameters, you can yes, you can use yPredict from this grid search dot predict grid search because it will give you this grid search with the best parameters, right? So you can use this model for doing some predictions, and you can print, I mean, X Y test and Y predict. This one will Y test, Y predict, and as you can see here, that the accuracy is we have one problem here, one classified as 2, one classified as 0, one classified as 2. And this one, it's one classified as 2, one classified as 2. We have a problem in class 1, one classified as 2, right? So we have 1, 2, 3, 4, 5, 6 cases out of maybe, I don't know. So the accuracy, we can see the accuracy. Yes. So if you want to check this, if you want to run this code, I can get it here, right? Open it in Google Colab. You need to run that part. So, I mean, working with this pipeline, it will make your life much easy, and your code will be more organized. It will be easy for other people to look into it and to understand it. And also, it will give you very good advantage to validate or cross-validate all those steps together, because it's difficult. If you run principal component analysis, you will select n components equal 5. Maybe you will get a question. Why did you select this one equal 5? So if you do it by trial and error, it will be difficult to convince people. But if you use the grid search, for example, it will be just say we use the grid search and we find that this combination is the best combination for my model. So we are plotting here. We use here principal component, n components equal 4. So we will get this graph as you can see here. So this is the explained variance from principal component 1, principal component 2, principal component 3 and 4. Total variance, of course, equal 100%. This is accumulative, right? So this is the accumulative one. I don't know, I cannot plot here. We need to create your pipeline. We need to import this pipeline from sklearn.pipeline. I have two pipelines, one with percept and one with adaptive linear unit, for example. All other steps are the same. If you want to display some feature, some steps, you just need to define it here, for example. So the first step here, it's min-max scalar. If you want to change some parameters, so you can do it here. So this is the pipeline. This is very nice also tool. So this is the pipeline. It consists of min-max scalar, standard scalar, principal component analysis, and at the end, the model will be a perceptron, right? And we adjusted the perceptron parameter here is 0.5. Principal component, because we didn't set the n parameters equal 1 or 2, so it's empty, for example. So we have this nice way. We need to define grid search, cross validation, and you can just put as much as you want here. You can put really very complex combination here for parameters, and it will help you to try to we'll try to cross validate. As I told you, we have 16 models, as you can see here. So we'll start with model 1 out of 16, correct? Out of 16, 2 of 16, out of 5, 7, 8, 9, 10, 11. So it's exhaustive search technique, in fact. So it will test all those combinations, right? So the grid search, okay, I don't know. So we have here minimax scalar. It was not a parameter. Principal component. They should mention here that what kind of parameters we are selecting. So if you want to get the best parameters, so it's a grid search.best score, for example. Best score, it will be 90%. So this is a cross validation score. It's 91%, as you can see here, 91%. And the best principal component was 3. The best eta, it was initial value, it was 0.2. So in this case, it's better to use 3 principal components, and the initial learning rate, it will be 0.2. So, so now I will set the parameter equal to the best set which we got, right? And I will retrain the model, and I will get the training score and the testing score. So it will be this number, right? Using 3 and 2, correct? Using hold out validation. Do you know this accuracy is much less than this accuracy, because we got the best accuracy here, 91%, but this one for cross validation, in fact. This one for cross validation. In fact, we should use here, when we are training this model, we should not use X train and Y train, we should use X and Y, right? So where it is? Okay, I mean this one here, it should be in fact X and Y, not X. And this is the average score. I mean, if it is higher also, it should be understood because we know that, so the accuracy now will be, we will see, because the accuracy now it's 90.7%, right? And also we still have the principal component, the optimum number of principal components equal 3 and the initial learning rate equal 0.2, right? We will train our model using hold-out validation, and we will calculate the accuracy score for the train and test set. And it's 83% and 81.6%, and it's less than the cross validation, because the cross validation, we got this mean value, right? And I mean the accuracy in cross validation, it's mean value plus minus standard deviation. So in fact, it's wrong to report this one as the average, but also it should be average plus minus. You can get those numbers because we have 16 models, so you can get the accuracy for the 16 models, for example, and you can maybe you can. This is the best. In fact, this is the best one, right? This is the best one, but we use cross validation. We divided our data sets into 5 folds, and we try to use cross validation. So for this combination, the average accuracy will be 90.7%. When we use hold-out validation, because when we use hold-out validation, in fact, we should not use hold-out validation again, because we have already the accuracy. So this is not, in fact, correct. So in fact, this one, it should be also X and Y, because we don't need to do hold-out validation anymore. In reality, we don't need to do this. So I will just print this one using X and Y, because we don't need to do this, because we already used the cross validation. So we don't need to use hold-out validation again, because if you will use hold-out validation, it's expected to get less accuracy because you didn't use the whole data set. So in this case, the accuracy will be 86%, right? Confusion matrix, precision, recall. If you want to get F1 score, it's the same, right? So you can do all this, right? If you want to do all this, you can just try to. So it's F1 score, right? So this one would be F1 score, for example. Maybe you can just do this. So you got all those numbers, right? F1 score will be 83%, right? It's combining precision and recall into one number, right? This is the same also for pipeline 2, correct? I don't know what is this example here. Classification data set. Make classification. I don't know what is this make classification in some. Maybe it's a data set which can be used for classification, for example. It's a little, I don't know. Maybe no problem. Just don't care about it. Okay, so this is a machine learning pipeline. So please try to use this machine learning pipeline because it's a nice tool and it will help you to make your work more organized. I'm not sharing. Can you see my screen?
Yes.
Okay, so you can see my code and my Google Colab, right?
Yes.
Okay, thank you. So do you have any question for this pipeline? So I guess also when you are working with deep learning, it will be also very smart to use this pipeline because it will work. It will make your work organized. As you can see here, we can just try to. Okay, where it is. So we can just use. Where is this code? Okay, now I closed it. So I mean, life will be much easier when you try to combine all those steps together into one pipeline and try to cross-validate all those steps together. Your work will be more organized and it will be much easier for people to reproduce and to understand your work. Yes. Do you have any question, please, in that part? Any questions, please?
At
So
least I can just
Mhm.
comment that I think it was nice to see. I didn't know about this pipeline tool.
Yeah, thank you.
I've been doing the same mistake that I've been doing a grid search on hyperparameters, but I could not include, for example, number of principal components.
Yes,
or hyperparameters from earlier in the pipeline. So
yes.
This is very good.
Yes, thank you very much. So it will be really very nice because it's a habit. In fact, when we do, because also I have been doing this all time without using this pipeline, and it's difficult for people. If you have a mistake in the code, it will make a problem for other people. So it will be nice if you can get all those things together in one pipeline, and it will help you also to answer questions. So imagine that you are in a defense and someone asks you, why did you select, for example, n equal 3 or 4 or something? Or if you are using select k-based, for example, those questions, it's difficult to answer. You cannot say also it's by trial and error, because I mean, it's not good answer to say it's by trial and error, but it will be nice to say just yes, I use the grid search, for example, and we try to optimize. And this is the optimum set of components, I mean, of hyperparameters when we use the grid search in our pipeline. So it's very important to be prepared for. Just imagine that you are defending your thesis and you have someone who is asking those questions. So it's better really to answer those questions today and to, consider those into your writing or, results section in your paper. For example, you need to just put something. So you just close the door. You will not get any questions in that part because it has been done in the correct way. Also, please, because I attended some PhD defense, and people also in the same paper, in fact, people can report a result of a model as a range and some other results as a number. And it's strange because if you will get this mean plus standard deviation, for example, or confidence interval, you should be consistent and you should report you can report all other features also or other metrics in the same way as a range, for example, and try to understand what is the meaning if you have mean plus standard deviation, because they can ask you how many times did you run your code, for example. You can say one time, but one time, how can you run it one time and you can get a mean and standard deviation? When you get mean and standard deviation, it means you ran your code, for example, you tested your model maybe 10 times or 20 times, for example, 10 times. So just be prepared for it. If you will use confidence interval, you will be safe. You can just say we ran it only one time, but we use the confidence interval and we calculated it using this approach. So we can have a range and at the same time avoid running the model several times because it takes too much time, for example, for training and testing, for example. So it's very, very important to spend some time and prepare your results in the best way. So you can just be ready for any question in that part. Usually you are getting those questions from reviewers when you submit your paper and also in the defense itself. People ask those questions and in the defense, imagine that you wrote a paper now and after 2 years you will defend your thesis. So it will be a long time. So maybe you forgot all those details. So it's nice to have all those details into the results section. So you will be ready for to answer those questions. And it will be easy also for people who are reading your articles to understand it. Yes, so thank you very much. We can take also again maybe 10 minutes break. Is it fine? We can start again at 12 minutes this time. We can start at 1. Is it okay?
Okay.
Yep.
Okay, thank you. So see you after 10 minutes or 12 minutes.